Okay, so as we now get into our very last topic of the course, I'm going to talk about multiple regression for today and next time. And it's not connecting. There it goes. So very often we're interested in simple one-to-one variable relationships, height and weight, very simple things like that. Education, income, whatever. Let's say we have a relationship between years of education and income, which is about, let's say that the R, the correlation coefficient, is 0.5, which would be pretty high. Okay? So let's say we have something like that, and that graph the other day was more like about a 0.8, so it would be a lot more scattered. A 0.5 looks more like that's a 0.5, roughly. Looks like something like that. That's probably more like a 0.6. That's still close. Okay. Now, R equals the covariance of x and y divided by the standard deviation of x times the standard deviation of y. Right? So how much variance is accounted for by one variable in the other? In other words, how much variance do years of education and income share with each other? Okay? So shared variance. How much can we explain? How much variance in income can we explain by variance in education? You have to start thinking of variance as a thing you can touch, which is kind of an odd thing to think about. I'll give you a couple sort of analogies here as we go along. Well, in fact, R deals with standard deviations. So if we want to get variance, we're going to square R. We're going to get R squared. So we would have 0.25. Right? So 0.25. So we accounted for 25% of the variance in income by looking at variance in education. And 25% of the variance. That means there's 75% of the variance left to explain. We've explained lots, but we've got a lot more available to still explain. So we still have 75% of the variance to explain. Make sense so far? Think about this. If we had height in centimeters and height in inches, height in centimeters explains 100% of the variance in height in centimeters. They're the same thing, just measured in different units. We're trying to, at some point, it would be great if we could explain all the variance in some variable as some combination of variance in other variables. Then we could actually predict perfectly the variance of in some variable by looking at the variance in a bunch of other variables. That's what we're trying to do. Okay? So, there must be other variables that account for that other variance. We don't know what they are. We don't know what they are. We can make some guesses. We don't know what they are. The way we deal with this is we bring them into the model as well. So instead of just saying y equals a plus bx, or I'm going to start today saying b sub 0 plus b sub 1 x sub 1, we're going to bring in another x. Okay? That's all we're going to do. Sorry, it was very concerned. You okay? You should try sleeping. It's an important biological function. Also, I don't know if you've seen the Star Trek The Next Generation episode, They Don't Sleep. Next thing you know, Counselor Troy will show up in your dreams and talk to you about height. Don't watch that episode. It's awful. TNG is really into this. It's really all Star Trek. When you make a million TV shows, a good chunk of them aren't going to do that great. That was kind of weak. So we deal with this now. We're going to by bringing that into the model. So we're going to, here's a picture. That's the variance in y. That's the thing we're predicting. So again, think of variance like a thing. So that circle represents the variance in y. So there's x1, and it overlaps, that's about a quarter, it's probably a little less, but let's pretend. x1 overlaps about a quarter with y. They share some of their variance. Okay? Just a classic Venn diagram. They just share variance. But you see, there's all this other variance in y we haven't accounted for. And perhaps that's accounted for by x2. So if we bring x2 into the model, we are now explaining more of the variance as a combination of x1 and x2. So, I don't know, what's something else? So we got, if y is income and x1 is years of education, what's something else that explains income? That we can measure?
Their parents' income?
Yeah, that's good. Sure, parents' income. Yeah, it's probably not that high, but let's just for say whatever. Let's say it's parents' income. That's good.
What was the other one you said?
This would be y is the overall your own income. This is years of education for x1. x2 is going to be how much money your parents make. Years of experience in a job. That's another possibility. There are all kinds of things we can bring in to keep explaining more variance. That's right. So now we've explained, I don't know, looks like maybe it's not 50%, maybe it's more like about 40% there, but whatever. The idea here is to explain as much variance in y with as few variables as possible. Okay? That's what we're trying to do. There's also variables that have no relationship whatsoever with y. Length of your big toe probably does not really matter a lot. But it probably matters a little bit because men make more money than women and men have bigger toes than women. Let's pretend we live in a perfect world where there is no sexism. We have smashed the patriarchy. And now we don't care about any of that stuff, and the world's great now. So toes don't matter. Hashtag all toes matter. So basically, strangest thing I think I've ever said. So, and there's a lot of candidates, man, I'm just saying. I'm getting a little punchy. It's a time you're ready to get a little punchy.
We say that every class.
Yeah, well, since about January. Early in the term, like early in the year, no, I'm just, yay, teaching, I'm a scientist. I like it. The first term's great. Second term, I have enough of you people. Second term. So, anyway. So, did you see the point, though? Okay? We're trying to explain as much of the variance in y by looking at variance in other variables. We're trying to explain something, to make a prediction, to talk about how the universe works, which is kind of a cool thing. Okay. Of course, I'm going to turn this into, instead of pretty pictures, I'm going to turn this into a model. Yes, David?
Okay, so the last one, you said the first one was r squared, and so it was 0.25, right?
That's right.
So then the other one, you would do the same thing, and then that would maybe be like 30% or like...
Or something like that, yeah.
whatever.
Yeah.
So you just basically, let's say you have like 10 things,
Yeah.
and then they add it up to more than 100.
That would be a problem. Because they can't add up to 100%. You can't explain more than 100% of the variance.
No, I mean, but if they're across.
Yes, they overlap. If all the x's overlap with each other, you mean?
Yeah.
Yeah. Theoretically, that's not supposed to happen. We hope that doesn't happen. I will talk about how to detect when that happens. Because the model, this is good that you're thinking like that, because that's what Dane is saying, if you're not sure on this, is that I showed you an idealized situation of how the world could work, which would be, if only it were so, we have y, and we have x1, and x2, but what if we had x3 and it was here?
Yeah.
Yeah. It's not accounting for unique variance. Some of this variance isn't unique. Some of it's overlap, right?
Yeah.
Yeah, that's not going to be good.
Because like for income, you would have like a million variables.
Oh,
that
sure.
would contribute
And
to
think
that.
about years of education, IQ points, which overlaps a lot with years of education. Because it helps you to get smart, to learn things. Also, it's hard to learn things when you're not that smart. Story of my life. So, if you put those two things together, they're going to overlap a lot. So we're going to hope that doesn't happen. And theoretically, right now, we're going to just assume it doesn't. But there are ways to detect it. We want as little of that as possible. Because we want to explain unique variance.
Because we could easily just say, okay, well, it's due to like socioeconomic status and your parents' income, but then we're not even like considering a million other things.
Oh, yeah,
that would
I know.
potentially have more.
Yes, of course.
Yeah.
Those are potential pitfalls that we can deal with. There are ways to detect this, and we can deal with it. The world literally never works with x1 over here and x2 over here. It can if you design an experiment and x1 and x2 are independent variables and y is an independent variable. Yeah, then, yes, sir.
At what point do you have so many variables that you can perfectly predict out your data, but you can no longer extrapolate it to the real world?
When you have as many, I can tell you exactly when it is. When you have as many variables as you have data points, you exhaust the degrees of freedom. You can predict perfectly, but you have a useless model, right? So if I said that I think I said this the other day, if I said I can predict all of your grades, and let's say I could probably build a model that could predict your grades, and I could base it on a few things. I could base it on, I don't know. I could give you all IQ tests, that would probably account for a lot of variation. I can do a few other things. And eventually, though, there's the ultimate variable I can get, which would be, what's your name? And then I'll just look it up. That's a useless model. I can predict your grades if you tell me your grades. Pretty good, right? Science. Call Nature and Science. I'm getting publications in both places. So yeah, and usually when you exhaust the degrees of freedom, you've got a useless model. Yeah, that's a good question. So in general, we have here's y hat. This is the same model except from the other day, except we've extended it. This is all we've done. So equals b sub 0, that's what we used to call a, so that's the intersect, plus b1x1, b2x2 plus dot, 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 plus b, p minus 1, x, p minus 1, time, plus e. We have p minus 1 predictor variables. Not p, but p minus 1. Okay? So we have p minus 1 predictor variables. We have p terms because we have an intersect. If you go on to graduate school, you can learn about times when you force no intersect. There are reasons to potentially do that. We're not going to worry. There's a lot of variations on themes you can do here, and we're not going to worry about doing variations on themes in regression. It's too late in the year. And also, most people don't do that. There are times when you might. So we have p minus 1 predictor variables. So this is for the data set itself. These are statistics. These are not parameters. These are predicting a parameter. So these are Latin letters. They aren't Greek letters. When you start seeing Greek letters and capital letters, that's when you start getting parameters, right? Okay. In the population, we have this. Y equals beta sub 0 plus beta sub 1 x sub 1 plus beta sub 2 x sub 2 plus dot 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 beta sub p minus 1 x sub p minus 1 plus epsilon. So that's the population. This is different. This is what we're trying to predict. Okay? We're trying to predict that with our data set. Oh, by the way, error is normal. Individual differences. It's not error, actually. In this case, is normal and independent with a mean of 0 and a variance of sigma squared. So that seems familiar, just like you have in the notes. So variance. So this isn't prediction error, it's individual variation. E, the residuals, those are prediction errors. That's when you've made a mistake, your model's made a mistake, you can't account for it. This is saying there's extra stuff left over. But it's not a prediction error, it's saying it's extra stuff, because this isn't a prediction. This model is not a prediction. This is actually how the universe works. Okay? So that's not a prediction. its individual variation. What's left over, basically. Okay. Questions so far? Okay. So you're with me so far? This is good. Please.
So, okay, so every single time we add another x,
Yes.
we add b2, or b3, x3,
Yeah.
b, whatever.
Yeah. That's right. So you have many x's, many x variables. X's are just predictors, not predicted. Y is the predicted. Okay.
Would these change if it's B0, B1, B2,
Yeah.
are they different numbers?
Yes, they're coefficients. And they're all calculated the same way generally that I showed you the other day. We don't have to worry about that. What they are coefficients that you multiply a number of times. So when you think about it, we're talking about how you calculate salaries here. And there's the intercept, which is the salary floor, and then there's some number, which was, I think I said 2, times the number of years. Years would be x, 2 would be b.
Oh, okay.
Right? So these numbers are what we're interested in. We're interested in, sometimes they're called beta weights, which is a stupid name because we're actually doing, they're really b's, they're not betas, but everybody calls them beta weights. So like if this is chi-squared, is that chi-squared? That's crazy, but I mean, whatever. So people call those beta weights. You're trying to predict, so if we had years of education, it's some number times your years of education predicts your income in dollars, whatever. So that's what we're trying to get at. Because it's never just going to be a combination of, like, just think of height and weight. It's a very simple one. Right? I'm, how tall am I in centimeters? I don't know. How tall I am in inches? 180 something. 182 something. Okay? So my weight in kilos is probably, about 85. So if I'm going to predict my weight from my height, I've got it 180 divided by 85, so I don't know, whatever the hell it is, 0.7 or something. That's the B. See? Okay. And of course, we're using me as the ideal specimen of humanity, so we can now generalize to all people. I'm sort of Schwarzenegger-esque, really. The California, the governor of California. All right. Questions? Good? So y, this isn't y hat, which is predicted y. This is just saying y is a variable, which is a linear combination of these variables times some bunch of constants, which are these b's. We get the y hat thing, but really what we're saying is we're predicting that, out in the world, it actually does work somehow. We just don't know. If we knew this, we wouldn't have to do this. Okay? Okay. So what do we get? If p minus 1, the number of predictors, is 1, we get a line. Right? We just get a line. Piece of paper, I did good. So we'll just use. If p minus 1 equals 2, so if we have 2 predictors, we get a surface or a plane. Okay? So there's an x this way, right? Left and right. But there's also now one in an m. So now we get a plane. Did you ever actually, did anybody here do 3D coordinates, Cartesian geometry in high school? Yeah, sure you did, right? Or you forgot it, but you did it. Because I think they still teach that. What do they teach in high school? Using Google and showing up? Is that basically what it is now? That's what it is.
Can you remind me of little frog beanbags that we used? Well, that's all I remember.
That's all you remember from high school?
All I remember was
Wow.
beanbags.
Did you eat a lot of mushrooms or something in high school?
Not mushrooms.
No. No, because you did math.
Not that. Okay.
Okay. So how, out of curiosity, how much math did you do? How many people here did math all the way through 12?
I did always see it.
Okay, yeah, I did grade 13. I did 3 maths. Okay. But most of you didn't do math all, but half of you didn't do math all the way to grade 12. There's something bad about that. I'm not saying to you, you were advised poorly. No, seriously.
I agree.
Yeah, guidance counselors are great. They knew so much about careers, why do we need guidance counselors? Heyo! It's a joke. It's a joke. It's a horrible joke. I'm sure they're fine people.
Can you explain to me how you visualize that again?
So, look at this. X and Y is like, you know what X is? Left and right.
Yes.
Y is up and down.
Yes.
The world, our universe, look around us, has 3 dimensions.
Okay.
Now we have another one coming in. So it's 3D. Right? So it's basically just, if you did do 3D coordinates, Cartesian coordinates, it was X, Y, and Z.
What was the Z?
That's up, out, and back. Left, right, up, down, back,
Instead
forth.
of paper, it becomes a cube.
So where's the data point then? If you look at this and then this.
Where's the data point? Because it's got, well, it's got 3 things. It's got X, right? It's got Y, and it's got Z. So it's here. It's floating in 3D space. And then it becomes a surface. It's a surface.
Oh, it's like a ribbon.
More like a piece of paper. A plane. Okay.
You can use the tables if you have like this is your X coordinate, this is your Y.
Yeah.
Is that coming
There you
from
go. The table works. That's right.
Oh,
Yeah. See? So here we go. X,
yeah.
Y, X1, X2, Y.
Then like, one would be like here.
Yeah.
Yeah. Or here, or here, or here. And then it makes a plane.
Okay.
And it has 2 slopes. It has a left-right slope and a back-forth slope. And those are the different P's. Those are the slopes. Right? You said you were learning 3D coordinates, Cartesian coordinates in high school. Why am I learning this? Because of right now. I'm never going to use this. Ha-ha! I will now call all your math teachers and say, I proved you right.
I think it was out of high school by the time I went through because I never did that in Christian university.
Yeah?
I think it was about,
I did it in grade 13 functions and relations.
I did OEC, calculus, and algebra.
Okay.
I didn't do finite, which was the 3rd math at the time.
Okay.
But then I did university level calculus 1 and 2, and I did it in those classes.
Yeah, I mean, we had, when I was in high school, it was grade 13, we had, it was 3 maths you could choose from, algebra, calculus, and functions and relations. I did all 3. I did functions grade 12, because everybody did.
I had to do a French class, so I couldn't do
Ah.
that because my year in France as an exchange student didn't count towards Ontario French credits.
Yeah, because they don't speak French in France, so.
At all.
Yeah, there's no French there.
Yeah.
Makes a lot of sense. So, point is, you get a surface. If p minus 1 is greater than 2, you get a hyperplane in hyperspace. Stop trying to visualize.
What?
You can't visualize a hyperplane in hyperspace. Because now, what we could imagine, think of this, is x3, so x1 and x2 we get a plane. Now x3 is going to be time, so it moves. Dude! So I don't try to imagine that. Because that's wacky. And it could be changing color too, so it's bringing a don't try to imagine hyperplanes. I know people that can do that, and I envy their ability to imagine that and that makes sense to them. I can't do that. I can surfaces are easy. I live on surfaces. This is okay. It's when it starts moving, that's a little hard, but it's like if I imagine, okay, hang on, as time goes by, when it gets to like, now it changes color, and the cooler the color, the lower the number. Nope, I quit. I'm done. So in fact, you will very rarely see in a paper when they present a regression model anything other than a surface, like a 3D kind of graph, even though it's not a 2-dimensional paper, you can imagine it. You're not going to see a hyperplane, because nobody's going to say, now click on the video, and it doesn't help anybody. So your best bet with hyperplanes in hyperspace, and I just love saying hyperspace because it makes me feel like Star Trek again, is don't try to visualize them. It's really, because you're not going to be able to. If you can, that's wonderful. That's just not, I can't do that. Now, stats prof Ian there, the Scottish guy, he said he could do 4 X's because he could imagine colors changing and it moving. I didn't believe him, but he's probably right. It's easy, Brodbeck. It's completely intuitive. You're just changing colors. Time goes by. Really? You call that intuitive, do you? Well, thank you. That was very useful. Okay. So, you know what? Think about this. I can draw this. A computer program can draw me a 3D surface graph. Now I can't show you a picture anymore. I can give you an equation, and equations are great, and I can do that. But pictures are nice, and to me it's always a big step. If you're going from 2 predictor variables up to a 3rd and 4th, that to me is a big step, because now I can't draw you a picture anymore. So to me, there's like a jump you're making in complexity when you go from choosing 2 to 3. As soon as you put that 3rd variable in, I can't draw it anymore. Or I can't get a computer program to go draw it for me either. Right? So to me, that's a big step. I'm not saying that should be a deal breaker for you, but to me, it's a very big step when I can't draw the damn thing anymore. Okay? Of course, we're going to analyze this using ANOVA. It's about variance. Just when I thought it was they pulled me back in. We can find that if our regression model is significant using analysis of variance, because it's just about variance. So we have 2 sources of variation or regression, variance due to regression and variance due to residual. If you look at your output for analysis of variance with general linear model with GLM or SPSS or PSYC, it actually says model and intercept, if you've noticed. That's because it's actually doing regression and turning it backwards into, which is kind of cool. So we actually get something that looks like this. We get variance due to regression, has p minus 1 degrees of freedom. Residual has n minus p. N is the number of cases. Okay? And n minus 1 total. We take mean squared regression, divide by mean squared residual, and we get an f-value. This analysis is about the whole model. Maybe it's got 5 variables, maybe it has 1. Maybe it has 2, maybe it has 11. 11 seems high. This is not about individual variables. This isn't saying, if we go back to our original example, are we explaining a significant amount of variance in income with years of education? This is saying if we take years of education and parental income together, do we explain a significant amount of variance? Okay? So it's about the whole model. It's not about the individual B's. It's not about the individual variables themselves.
For the residual mean square, it's over P1, not N minus P.
That should be N minus P, you're right. Yep, that's right. Sorry about that.
I was like, why did that change?
No, you're right. Okay, yeah, that should be N minus P. Okay, so this is one thing that's the sum of its parts, the regression model. It's literally the sum of its parts, okay? But we want to do finer grained analysis here. What we want to do is want to find out, do individual predictor variables explain a significant amount of variance? Because the whole model will be significant. There's no way it's not going to be. You're not going to start be measuring, big toe length or something like that. You're actually not going to do that. So we're much more concerned with how much extra variation, extra unique variation, is accounted for by individual variables. So we want how much unique variation is accounted for in y by adding in another x. So if we had years of education and income, and we added in months of education, that's not accounting for any extra variance, because years are a function of months, right? So it's actually accounting for the same variance. It's nothing unique there. And that's an absurd example, but if we had something like IQ, which correlates pretty highly, that overlaps a lot with years of education, we might not want to use that variable because it doesn't account for enough extra variation. You get a value for the whole model called big R squared, which is sum of squares regression divided by sum of squares total. It's the total amount of variance accounted for by the whole model. Big R squared. So if you have a model with 5 x variables and you add a 6th, does big R squared go up? Well, it has to. It can't go down. Because it's sum of squares. They're squared quantities. You're always adding in more a positive number. You could add, it could be 0, so it could stay static, but that's never going to happen. So what we need is something, in fact, that looks at when an extra variable is added and corrects for the idea that it's always going to go up. So we have something, well, first of all, you should realize that the question is, how much does it go up by? And is it enough? And is it enough to deal with the loss of degrees of freedom and the increase in complexity? Every time I add another variable, I'm telling you the world's more complicated and it gets harder and harder to understand. So if I say that y is a combination of some constant, b sub 0, plus a bunch of constants times a bunch of variables, that's fine. If it's like 2 variables, you deal with that. If it's 11, you start going, oh, right, so you're not helping me much. Because we want to be simple enough that it can be understood, and we want to have a lot of explanatory power. It's always going to go up, but is it enough? Is it useless to throw that other variable in? So we need something other than big R squared going up, because it's always going to go up. So we have something here. I'm never going to ask you to reproduce this for me. I'm telling you what this thing is. Adjusted R squared is weighted by the number of observations and the number of variables in the model. So it's adjusted R squared. It can go up or down. So it's weighted by the number of variables in the model. So we can go down when more variables are added, if not very much is explained, but we've got another variable. So it can go down. So on a very simplistic kind of level, one of the things we're going to look at is adjusted R squared. Okay. Questions? Okay. So when we're doing this exercise called model building, we are going to be comparing different models predicting a y, and we're trying to determine which is the best model. That's always the question we're asking. And in fact, the question on the final exam, this question here, 6A, I will be giving you a whole bunch of stuff and asking you what the best model is and why is it the best model. That's what that question is going to be. Okay, so here's a model with just x1 in the model. and of course an intercept. And I'm saying that for regression, we got 1 degree of freedom, and for residual, n minus 2, p minus 1, n minus p. Sum of squares are 50 and 80. Put that one over there, bring this one here. This is x2. This is a different variable. Sum of squares 30 and 100. Of these two, not even looking at the final one I'm going to bring up, of these two, which is the best model? Which explains the most variance of those? Is it the one with just x1 in the model, or the one with just x2 in the model? What explains the most variance? What's r squared for the first one compared to r squared for the second one? So we're going to take sum of squares regression and divide it by sum of squares total. 50 out of 130, or 30 out of 130. Which number is a bigger number? Well, it's 50. This isn't tricky. The one on the left, x1, it explains more variance than just x2. Right? It's better. But what if we put them both in together? Aha! That's x1, x2. And these should be moved over, but I changed the size of the slides. This is perfect for 4x3. Change it to 16 by 9. This explains 80 out of 130, which is more than 30 out of 100, and more than 50 out of 130, more than 50 out of 100. Note a few things. The total sum of squares is the same for all of them. Okay? But they have different regression sums of squares because they're different models. Now, of those three, which is the best model? This isn't that complicated because it's just got two predictor variables, x1 and x2. So it's not like you're going from a surface to some sort of weird thing you can't imagine, so I can even draw a picture of it. That's nice. The complexity isn't bad. It's only got two variables. It's explaining 8/13 of the variance in y, 80 out of 130, compared to 30 out of 130, or 50 out of 130. Those are good. Right? Do x1 and x2 explain unique variance in y? In other words, is there any overlap between x1 and x2, or are they explaining unique variance in y? You are correct. Why is it unique?
Because the sum of the squares add up to their actual total.
Yeah.
It's not a smaller number.
That's correct. You guys get that?
No.
Okay. That's fine. The fact that anybody picked that up is nice. This explains 5/13 because it's of 130. Okay. X1 explains 5/13 of the variance in y. X2 explains 3/13 of the variance in y. Because 30 and 100 is 130, 50 and 80 is 130. The total is 130. That's all it is. Does that make sense so far? I'm glad you asked. This is good. You should ask questions, even if and you look at it now and go, oh, it's pretty obvious. Yeah, but I'm glad you asked it. That's what you're supposed to do. Okay. Now look at x1, x2. 80, 8/13 there. And 80 is 30 plus 50. They can't be overlapping. If x1 and x2 were overlapping, it wouldn't be 80, it'd be 65 or 71 or something bigger than 50 and less than 80. It has to be bigger than 50 because that's the big smallest, like that's here. And it can't be bigger than 80 because that'd be the total. So if you think of it like the overlapping, or if you think of it like a container. So this is all the variance in Y. Okay? When we put x1 in, we've explained some variance. What we want to happen is when we put x2 in, it explains unique variance. But let's say we have it, and that's we have it. Now, those aren't the scale, but whatever. Now, when I bring in, let's say x3, let's say it does not explain unique variance, that it has some overlap with x1 and x2 already in the model. There's x3. It actually overlaps with x1 and x2. Yes?
Now, if that were to be shown on there, let's say x3, so like
Yeah.
RG, let's say 30,
Sure.
RS 100, and then
Yes.
for x1, x2, x3, RG now is 90 and
Yes.
RES is 40.
Yeah, that's right. Because it should be 110 because
Yeah.
you said 30. Yeah, exactly. And it would be, because if it was unique, it would be 80 plus the 30 from x3, but it's not if it's less than that. In that case, you'd say, oh, that's not as good, even though I'm explaining more variance. We want to explain variance. We want to explain unique variance. We don't want to explain the same variance. And again, think of the absurd example. If you bring in, if we're predicting weight from height, and the first variable is height in centimeters, the second variable is height in inches, it literally is going to explain exactly the same variance. It's going to be x1 and x2 will be the same as x1 or x2 because it's the same variance. Your height in inches is just another way to measure your height in centimeters or your height in pennies. So you said they had a pile of pennies and use that to measure your height. So what we want is to explain unique variance. We don't want to explain the same variance or variance we've already explained. Questions so far?
I'm sorry, I still don't understand the 130 thing.
There's 130 things of variance.
Yeah.
Okay? That's the sum of squares for one. The whole thing. There's 130 units of variance there. Okay? You see that because when we add the sum of squares for any of those, it's 130. It's the sum of squares total. Okay? Now, we want to explain as much of that 130 as we can. And we are explaining that. The way we can see how much we've explained is by looking here at the regression sums of squares. So we want to explain as much of 130 as possible, so we want that regression part to be as high as possible. We also want it to be explaining unique variance. So the beautiful thing here with this cooked up example that would never happen in real life is that for x1 we have 50, for x2 we have 30, for x1 and x2 we have 50 plus 30, we have 80. We actually explained unique variance.
So they don't overlap.
They don't overlap at all.
And so when you were saying something, Sean, that you change the numbers and then it goes to 110.
So I added another variable that
So that's three.
explains 30% of the total.
Yeah.
However, when I add the three together, I only added 10 of that, which means 20 units of what it explains.
Whatever it is, yeah.
It's explained by either one, the other, or both.
Or both. Yeah. Some combination of three. Yeah.
It's like what I said, only like a third of what I found
Yeah.
is unique.
And in that case, we likely would not use that model because we'd say, well, look, we've got a two-variable model with all unique variance. The third one doesn't explain a whole lot extra. I'm not going to use that. So you see a lot of this is you're going to be making judgment calls when you do regression stuff. It's a little different. You're looking at it going, it's not, is this significant? It's almost always going to be a significant value. It's, does it matter? Does it explain unique variance is what matters. Because again, if I was explaining height and explaining your weight and your height in centimeters, your height in inches, both of those explain a significant amount of variance. But one of them, they completely overlap, so just use one. We're trying to account for unique variance in what we're predicting. That's the point of this. And if we can do that and present it as an equation to somebody, Yay. So this is how the world works. Other questions? That was good. Does that make a little more sense now, Dan?
Yeah, it does.
Good.
I get what you were, just when you said that, I was like, wait.
No, when you think of it, like I said, like a container full of variants or something like that, whatever works for you, right? Please, gotcha.
How much unique variance do you need for it to be considered a good model?
That's a question that there really is no answer for. That's the thing. Because the whole model is always going to explain a significant amount of variance. If it doesn't, I don't know what the hell you're measuring. Right?
When we have to make the judgment call for on the exam, what would
Oh, no, that's not what you would be. See, the thing is, that's not the kind of judgment you end up making in these things. The judgment you end up making is, which of these models does the best job explaining the variance and why, not was this a complete waste of time? So, the kind of questions you're asking with regression are different than the kind of questions you answer with, say, analysis variance, even though you're using it to do the same thing. The question you're asking is, can I predict y from as few x variables as possible? Right? And can I do that by explaining as much unique variance in x, in y, I'm sorry, every time I add another variable? When you look at these things, you do them, these are much less fishing expeditions than ANOVA is. When you do an analysis of variance, a lot of times you say, okay, what happens when I put these two groups together? Here you say, I know things happen. Can I explain how they work? It's sort of a different kind of question. They're intimately related, of course. But they're asking a different kind of question. This is building a model of the universe rather than saying, are there effects or not? So it's a subtly different question. Good question, you just asked. Other things. Would you like to stop for today? Yes, I hear a chorus of yeses. That's fine. We have enough time. We can do that next time. We can finish up next time. And except if you're watching on the video, I'll see you on Tuesday. If you're watching on the video, there's another slide coming. Okay. So this is where we were last time talking about the different models. And whoops, let's go back. So we had the different designs, or not designs, sorry, the different regression models, which that one just moved, I don't know why. But basically the idea of ever having the three different ones, right? And which one is the best model, and making that kind of choice is something that you end up having to do all the time with regression. And it's basically just to see which model is the best one. The whole model itself is always okay. It explains a lot of variance. It's a question of which one do you want to use. Okay, so those sums of squares. Remember we talked today about analysis of variance and doing sums of squares for cases where you have unbalanced designs, missing values, things like that. So there are type 1 and type 2 sums of squares. We talked briefly about those the other day. The type 3s are what we usually care about in ANOVA. Type 1 sums of squares, this is where this actually is useful, is that type 1 sums of squares depend on the order things go into models. You might think, well, that's useless. No, it actually isn't in this case, because it's going to say, have we accounted for unique variance? Okay, so let's say we have a three-variable model, x1, x2, x3. Okay, so we have a three-variable model. We have a data set with three variables, and we want to take a look at how much unique variance is being explained when we bring x1 in, how much unique variance is being explained when we bring x2 in, how much unique variance is being explained when we bring x3 in. So if we look at this, if we were to compare these, whoops, what just happened there? If we were to compare those, it didn't show up. It's right here. It probably works fine on the YouTube video. That's great. So I can draw it on the board. So we've got, let's see, type 1, type 2, type 3, right. So if we've got type 1 and type 2, there you go, and we've got x1, x1, x2, and x1, x2, x3. The type 1 sum of squares for regression is going to give you just with x1. The type 2 is going to give you x1 and x2. And this is going to give you for x1, x2, and x3. Basically what it's saying is when you get this, the sum of squares regression, it's going to give you all these things. The cool thing is, that's, where'd my eraser? Not my eraser, where'd the eraser go? Messed that up. Yeah, that should be just like this. Okay. That's for x2, that's for x3. So that's the thing that's calculated. For type 2s, the cool thing here is it's x1 given x2 and x3 are in the model. x2 given x1 and x3 are in the model. x3 given x1 and x2. Okay? So what that's doing, you can see that the type 2s actually look at unique variance. The type 1s actually don't. They're basically just giving you the whole thing. And in this case, we're saying we put x1 in first, then x2, then x3. So if you think of variance like a thing, variance in y, we put x1 in, and then we do x2, and I don't know, let's say x3 is really good. In the best of all possible worlds, nothing overlaps. This is literally never going to happen, but you can pray to the regression gods, whoever they may be. What you're more likely to get is something like this. There's x1. Let's make it the same amount. There's x2. Oh, we got some overlap. And x3 maybe overlaps with both of them. So that goes down to all that. So the thing on the right is more likely to be that, where it overlaps more, where we get overlap between the different amounts of variance explained in y. I knew that wasn't showing up. It's very annoying. It never happened. Oh well. So you can see, you might think, well, why would I ever look at type 1 sums of squares? Well, what they basically are different iterations of the model. Well, here's what it is if I just have a one variable model. Now let's see if it's a two variable model. Now let's see if it's a three variable model. The type 2s are saying, we're going to assume it's a three variable model. Here's those first two are already in. Now we'll look at that one variable on its own. So you might ask, why should you care, and hope that the thing comes up good. If there's no correlation between the variables, in other words, no overlap, the type 1s should equal the type 2s. So in fact, when you look at an output and you see that there's the type 1s and type 2s are roughly the same, you should be happy. Oh, good. It accounted for, it's mostly unique variance. That's usually not going to happen, but you want it to be as close as that as possible. Okay. If there is a correlation, the type 1s don't equal the type 2s. Of course, there's also an easy way to find that there's a correlation. You do a correlation matrix, and you just have all the variables on either side and see if there's a correlation. That's all fine. We'll talk a little bit more about that later. I had to put this in at some point, so I put it in now. About the correlation stuff. So what can these type 2 sums of squares give you? So type 2s give you extra variation, extra unique variation that is accounted for by bringing a variable into a model that already has stuff in it. Like it says, oh, that other stuff's already explained. What unique variance is this variable explaining? So if we look over here on the right with the overlap, it's saying, and it's doing it for x3, it's going to tell you just what this is, right? And nothing else. Okay? So that's for type 2 sums of squares, and if you play around with SPSS or any stats package and take a look at the sums of squares, some of the options, one of the things you always choose is, well, I want to look at the type 2 sums of squares. Just a little click, and it does it for you. This can give you something called the coefficient of partial determination, which is kind of like, well, it's kind of like R squared, but kind of the opposite, because R squared's the whole model. This is just this one thing on its own. How much does it explain? Right? That's basically what it gives you. And of course, it can range between, this coefficient can range between 0 and 1. It's kind of like a correlation coefficient in a lot of respects. So this extra variation is what you're into. So the coefficient of partial determination gives us the extra variance explained, accounting for the other variables. It's sort of like you're statistically controlling for something. Okay. It's a measure of extra variance explained only with that variable. So if we think back to the example we had, income, years of education, and IQ. And we said, IQ and income, or IQ and years of education clearly correlate. They overlap. There's no doubt. But there must be some unique variance that's explained in your income simply by your IQ if you've already taken care of your education. So it's kind of like controlling for it statistically. So we're going to see is what proportion, if we control for something else, we take all that variance out, how much variance is left that is explained by something, let's say, like IQ. So you can see why it can actually be a useful thing on its own to report the coefficient of partial determination. It keeps doing stupid things. Things come up and they disappear. You can square it and get a partial correlation, which is actually pretty useful. And you probably see partial correlations. They're just correlations that control for something. Or sorry, take the square root of it, not square it. Because it is little r squared. Given something else, basically. Okay. I don't know why this is doing this. Very annoying. Sorry. So why does this matter at all? Think about the model. Now I'm just happy whenever it doesn't disappear. Y hat equals b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus dot 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 b sub p minus 1 x sub p minus 1 plus e. Okay? So that's the model. It's a linear combination. It's additive. There's nothing in there about two variables acting together or overlapping, is there? There's nothing there that says, and also x1 and x2 together. In fact, so clearly that's an assumption of this whole thing. The math behind this is making an assumption that there's no overlap. And we know that that's really not true. We just don't want to have so much of it that it's a problem. So there's nothing in there about two variables acting together. And that's a thing called multicollinearity, when two variables overlap. Multi, more than one. Co, together. Linearity, in a line. Or even additive mod. So these things overlap, and we don't want that to happen. We don't want the x variables, the predictors, to overlap. Multicollinearity is actually a potential problem, because the model says there isn't any. And I don't know how you would build a model that says there's some, because then you have to know how much. And that's not an easy thing to guess about. So we want to not have multicollinearity. Because we're not supposed to. It says on the model that we don't have any. But we're going to have some. So you're violating an assumption. And we know that that's bad because it's going to make, what it does is it changes the values of the b's. It changes those coefficients. And we're trying to build a model, an equation that says y, whatever it is we're predicting, is this times x1 plus this times x2 plus this times x3. And we can now predict y. That's the goal of this whole procedure. And now it's going to make those wrong. So how do we detect multicollinearity? And this is what I said just a couple of minutes ago. One of the things we're going to look at is comparing type 1 and type 2 sums of squares for each variable. And really, even easier is to just look at the correlations between each variable, because the correlation coefficient is a pretty easy thing to interpret. You know, it's just a matter of how big in absolute value terms the number is from 0, and it can go up to 1 in absolute value. So you look at something, one of the first things you do when you do you try to build a regression model is you take your data set and say, run all the correlations possible. Just run them all, please. And that's easy for you to do, and it spits it out, and it gives you this nice correlation matrix, and it'll have all the x's and the y, and all the x's and the y, and you just see which ones correlate. You pick one are things that correlate a lot with y and don't correlate with other x's. Right? So you want things that predict y, but don't overlap with other x's. So probably if we had years of education and IQ, we'd look at that and go, okay, which one of these two has most overlap with y? And we'll use one of them, not both. Because probably the correlation between years of education and IQ is probably pretty high. Multicollinearity. So we're going to take just one of those variables and use it. So right away you have to chuck a couple variables. It happens almost all the time. Now, again, usually when you're doing a regression, you've got maybe 20 variables just to start with, or 100. You've got a lot of data, right? So you're saying, okay, I'm going to get rid of some of these anyway just to make my life easier. Just to start, I'm going to say, no, these two correlate to y. I don't want them. Those are bad. We don't want those. Let's get rid of them. Okay? And that's something you can do. It's not, there's nothing wrong with doing that. In fact, there's something very right with doing it. That's part of how that's where you start. That's where you start. Okay. Another assumption is, in fact, a linear model, meaning we only have, it's about straight lines. There's no curves. There's no, I don't know, sinusoidal functions. There's no exponential functions. It's all straight lines. But sometimes things aren't linear. The world doesn't always work that way. Think about something like, a lot of you guys took neuropharmacology with your half, right? Yeah, or you've taken brain and behavior with me. And you've seen a graph that I've shown of D2 binding efficiency and the ED50 for antipsychotic drugs, right? And it's a beautiful straight line, except it's actually not a straight line. It is an exponential curve. But to do a correlation coefficient, what the authors did is they took the logarithm of it and turned it into a straight line, which is totally reasonable. It's a standard transformation. So sometimes things aren't linear on the surface, but you look at it and go, I know enough math to know that's an exponential function. I'll take the logarithm and everything will be fine. There's a lot of log scales we use, right? Decibels for loudness is a log scale. The Richter scale for earthquakes is a log scale. Right? So a 4 earthquake, which is really not that big a deal, a 5 is 10 times more intense than a 4. And a 6 is 100 times more intense than a 4. And a 7 is 1,000 times more intense than a 4. So when you hear about something that's around, it's in the high 6s, and you go, well, I remember one that was, there was one here, when was that? About 10 years ago. And it was enough that, like, a little tiny few things shook. It was like a 3.9 or something. Yeah, exactly. It was one just very recently in Sudbury. And it's not that big a deal. You might go, no, it's weird. And then you move on. No, something fell off the shelf. Oh well. I remember one when I was in grad school, it was centered just outside Quebec City, and I was back at my house that I was running with my friends, and I heard something I thought one of my roommates had come in. And she didn't. Oh, something just shook. And then later, it turned out my mother-in-law yet, my what do you call your girlfriend's mom? I don't know what you call her, but that's who she was then. And apparently she was hiding underneath a table because it was centered near Quebec City. It was a lot stronger. But it was still only about 4.5. And then you hear, you hear people say when they see like a 6.5, well, I've been in a 4.5. Yeah, that's 100 times more, you moron. It's not just 2 more. Okay, so we do this all the time in science because a lot of things are exponential, so we can fix that. So, oh my God, what's that? You look at that and go, what in the hell? Well, this is some weird equation. This is actually an exponential equation. Okay? Y equals lambda sub 0 to the lambda sub 1 x e. Oh no. Now, you might look at that and wonder what the hell is that, but when you look closely, you realize we have something raised to a power, and it's raised to a power, in this case, look, it's, look, huh, that's a intercept, that's a, I think we can fix that. And you can, all you do is take the logarithm of both sides, and that becomes that. It just becomes a linear equation. It's beautiful. It just becomes a simple linear equation. And the way, how do you detect that? You look at it and go, S equals like this. Straight up like that, like reaction times often do, things like that, and you fix it. And this is one of those cases when you see something that looks like a pretty systematic thing, but it's not a straight line, and you think, I haven't taken math in a long time, go find someone who's taken math recently and say, what is this? And they'll look at you and go, it's an exponential curve. How do you not know that? And they feel bad, and they say thank you, and you walk away and get mad at them and say, I'm never going to help you, or if I do, I'll belittle your lack of knowledge of something when I do it. And then you take the logarithm, and the world is a happy place. Pretty simple. So this is called an intrinsically linear regression. The relationship is intrinsically linear. In other words, we can transform it. I just bit my tongue. You can transform it. No, taste any blood. Good. You can transform it into something linear. You know what? Have I told you the story about how I bled in front of a class once?
No.
My lip. Yeah. So, overheads, acetates, they're very sharp. And I have to look at things very closely. And I was pulling the protection stuff, and the tissue off the back, because it was brand new acetate that I had made. It was the intraocular, which is 1999. And I pull this thing off, and it's one of those document camera type things, and it's in a big classroom at Moore University of Newfoundland, and it's a big screen, and all you're seeing is blood drip. And you can see it on the screen. And that was awful. And I swear now and then, but I said horrible things. Horrible things, like words that had NF'er, a lot of that, and that was the kindest, most gentle thing I said. And then I had a cup of coffee, and it was hot. It was the beginning of class, because I just pulled the overhead. So I took my lip, and I'm putting it in this hot coffee in an attempt to cauterize the wound. It worked. Coffee had a really odd flavor afterwards. Well, it's coffee. You're going to drink it. Right? So, but yeah. And then I immediately went to the office of various administrators and said, I just said some horrible things in class today. But I've got a reason. I slit my lip and there was blood everywhere. Like, okay. And they're like, it's a little weird. So, but it was like blood. It was huge on the screen because it was a big lecture theater, bigger than like NW200 the screen. So like the screen was probably 11 feet tall. So there were blood spatters like bigger than my head. And I'm trying to clean it up, and I got nothing to clean it with. It was horrible. Anyway. It's one of my favorite teaching stories, It's like, and then I bled everywhere. So not everything is a linear relationship. There are some curves you look at them and go, well, that's not a straight line, but I don't know what that is. You take it to your math friend and they go, I don't know what that is. That's not a thing. We can't fix that. So you gotta be careful about that. Not everything's going to be intrinsically linear, but some things are. So you'll see something, I don't know. So exponential, or you might see something that looks like this. I'm realizing you probably take the square root of that because that's probably half of a parabola, right? And again, you probably don't have those kind of skills anymore because it's been a long time since you played with functions and relations in grade 12 or something, but you can look at that and say, I can ask somebody who does a lot of modeling or does a lot of stuff with math and say, what kind of curve is that? Right? And you can make it in a straight line. So there are times when you can fix the idea of a lack of a straight line, but you can't always do that. Okay, we also assume a fully additive model. There's no multiplication, no interactions. There's no something times x1, x2. Right? Big difference between this and analysis of variance is there's no interaction terms. I guess you could put in x1 times x2. But you have to be pretty sure that that's what the relationship is. That it's one times the other. It's not some other bizarre relationship, right? It's hard to know what the terms should be, and that's where exploratory data analysis, and again, talking to a real expert, right? Talking to somebody who has a bit of a math background, probably, or a pretty good stats background, can probably help you figure out, should it be x1 times x2? Could it be x1 to the x2? Like, you'd have to look at that kind of thing, and it's not always easy to do. Okay? It's not always easy to do. How do you select the predictor variables to begin with? Well, let's think about qualitative data first. When I qualitative, all I mean here are things that are nominal, they're categories. So it's not qualitative data like you think if you've ever heard of qualitative analysis where people just sort of, I don't know, read things and get a feeling for them or something. But it's when you have some hair color, right? Okay. It can be done if it's binary, because if it's binary, it's zeros or ones. Okay. So let's say it was talking about the smoking data I talked about. What if it's people who smoking is bad? So it's not that data set, but one of the variables is do you smoke or not? 1 is you smoke, 0 is you don't. Because the opposite of a smoker is a non-smoker. A non-smoker doesn't smoke. They get 0 on the smoker scale. So binary things are easy to code. We can have single variables and say zeros and ones. We can't do ones and twos, by the way. We have to do zeros and ones. Because this, remember, we're building an equation. So we can't have ones and twos. Are smokers twice the smokers that non-smokers are? Twos and ones? Doesn't make any sense. So it's zeros and ones. So if it's binary, it's easy to do. Okay? So zeros and ones, not ones and twos. There are ways to do things that are qualitative that have more than one value. So let's say it's hair color. And let's say we say that there are 4 hair colors. Okay, so there's blonde and brown and red and black. And we've rated things that way. Okay? Let's say we've done that. We have to do something called dummy coding, which is really annoying to do. But it's doable. So we now, instead of having one variable called hair color, we have 4 variables called blonde and red and brown and black. So if someone has blonde hair, they get rated 1 in blonde, 0 in red, 0 in brown, and 0 in black. If someone has red hair, it's 0 here, 1 here, 0 here, 0 here. This is black, etc. It's doable, but suddenly you better be damn sure this is a good variable, because we're now, every time you get more variables, in a potential model, you're making your life more complicated. And that's not something you want to do. You're trying to come up with a very simple explanation of something. So you can do what this is called dummy coding. You can do it, and it's perfectly fine, and people do it all the time, and it's annoying to do. Because now, let's say you said more than 4. I don't know, maybe you coded 7 different hair colors. Oh my God, you only get 7 variables. Right? You also have to watch out with Likert scales. Right? Things on a scale of 1 to 7. 4 being neutral, 1 being strongly disagree, 7 being strongly agree. Or something like that. Oh look, numbers. And people, as soon as they see numbers, go, well, we can do anything we want, they're numbers. No, you can't. That's the problem. Because the numbers, as I keep saying, don't know where they came from. The numbers think, it starts to lose its, the analogy gets weird here because I'm thinking about numbers thinking. The numbers think that they're numbers, and that 2 is twice the thing of 1, and 4 is twice 2 and 4 times 1. Except it's not. It would be like saying, I'm watching channel 4. What channel do you want? I'm watching channel 2. Oh, well, my channel's twice as good as yours. It's twice as the channel of yours. Makes literally no sense.
So like, they're numbers, but they don't have numerical value.
Well, they have ordinal value, but that's all they have.
Yeah. Like you could just as easily use A through whatever the 7th letter is, but people don't think about that.
No, that's right. And in fact, to do it properly, really, you have to dummy code everything.
Yeah.
And that's a royal pain, right? So when you use Likert scales, they really should be from, say, questionnaires or measuring instruments that have been validated all to hell. So when it's your own Likert scale, so let's pretend you're doing your honors thesis next year. And let's pretend you made up a questionnaire, and you made up a questionnaire measuring aggression. Because you don't want to use the 8 million perfectly good ones that are out there for some reason. And you say that someone got 38 on their aggression questionnaire, and another person got 14, and another person got 7. It doesn't mean an effing thing. Like it really, the problem there, it might mean something. It probably orders them, but that's all it does. With a really well done Likert scale, you can probably make an argument that you can think of them as kind of like ratio scales. We do this way too often. Right? Generally, people do this all the time. You gotta be very careful with Likert scales. I can tell you that if you wanted to use regression and you were doing your thesis and you had a Likert scale, you are getting a question from me. And the thesis questions is like this. But you get that question in practice well before you actually get it in public, and I'd say, please don't do that anymore. Because I'll ask you this the next one. Don't do that. Wrong. That happens every couple of years. Not every couple, every 5 years. Every year, this is my question in the practices. Where are your error bars? And they look at me and ask me, error bars, standard errors. Please go do that with your graph. Because I'm the error bar guy. Experimental variables can be great, like what group you're in, because there's no multicollinearity problem there. If you're in group 1, or group 2, right? And you have different levels, and I can measure them. I have the amount. Let's say we're doing levels of processing, and it's low, medium, high. Let's not do that. I have to code that. Let's say we're doing retention interval, and it's 5 minutes, 1 hour, 24 hours. So it's 5 minutes, 60 minutes, and there's 3,600 minutes. Yes. So I think that's right. No. 60 minutes times 24, 400, I don't know. But I do it minutes, so the numbers actually make sense. I can do that. And I can have other variables, and they're great. Let's say it's just low and high levels of processing. Excellent. Now I just want to zero level. Right? And I can just use those 2 variables. There's not going to be any overlap. There can't be. I built the damn thing. So you can use experimental variables. People do this. So it comes, once you've put all this stuff together, you're going to do something called model building. You're actually going to build a model. So how do you choose which variables to use? What's the process? So differently than analysis of variance, where what we're trying to do is say, is there an effect? We're trying to say, this is how the universe works. Those are two different kinds of questions. They're related, but they're different questions. You're making a prediction with multiple regression, not saying there's an effect of A or B or whatever. You usually start with a long list of variables. Okay? You could do all the possible regressions. The first thing you could do, literally, is do every possible model. Hey, look, if you've got 3 variables, that's not that hard to do. X1, X2, X3 on their own. And then X1, X2, X2, X3, X1, X3, X1, X2, X3. You compare them all. Well, yeah, that'll take you an afternoon. Like if you actually put it properly. That's 7 models to look at. I could compare 7 things. I've done this before, and I've had them all for an assignment. I've never actually done this in a professional career, but for an assignment, I remember in graduate school having them all laid out on the floor and looking at all of them. Well, this one's better for this one's better for this, and I can make it a judgment. For 4 variables, there's 15 models. I can do that probably. Because I can probably look and go, these 5 suck. We're not even looking at these. Now it's down to 10. Okay, I can probably do that. For 10, there's, I believe, the technical number is a zillion. I don't know how many it is. It's a big number. I once gave students, the first year I taught a course like this, I was in graduate school, right at the end of my PhD year time, and I taught this at U of T, and I told the class, okay, here's a data set, it has 21 variables, I want you to find the best model to predict this one variable. That's your assignment, that's all it is. I will tell you, please do not choose all possible regressions, because it will, first of all, this was 1993, we are allowed to print 200 pages a term. And secondly, it'll tie up to computers. Because it was all done on mainframes. And the number of calls I got from the computer center at U of T. Is this Professor Brodbeck? And it's like, oh, that feels good. I'm just a graduate student, that feels good. Yeah, sure. Did you tell your students are using up all the computers and all the time, and nobody can do any research? It's like, I told you people. And the guy called like every 5 minutes. So another student said, don't tell me anymore. I told them not to do this. Because it was literally trillions of models. It was 21 variables. All regressions. Yep, that's what I'm going to do. He said not to do it, but I'm going to stick it to the man. I don't know what that I'm thinking that is. So typically you don't do this. But if you can, it's great. Look at residual plots. They can be very useful. They can tell you when you have non-linear relationships. You can find weird anomalies, like you can find, oh, look, that one residual is way up here. What the hell's going on with that data point? Well, that's the guy who said he smoked 400 cigarettes a day. Right, and that was the data set that I gave those students. And that I left a mistake in there. Oh, if you find that, that's good. You can find non-linear relationships. So it's useful to look at residual plots. Individual x variables along one axis, along the x, and then the residuals, y minus y hat, along the y. And you want to see a uniform scatter. Okay, then you think, well, it's got to be an easy way to do this. Maybe there's some automatic ways. Yeah, there are. There are 3 basic automatics. They're algorithms. They will get you a model. There's one called forward selection. What it does is it starts with the x that has the highest r squared, in other words, the biggest overlap with y, and it puts it in the model. And then it adds variables. It takes the next variable that has the biggest jump in r squared. In other words, how much, not adjusted r squared, just r squared. So how much extra, do we have any more variance? Yep, throw that one in. Just an algorithm. It's doing this, the computer's doing this for you. It keeps going up until r squared doesn't go up enough. And of course this makes you think, well, what's the question? What's the amount of enough? Well, you can actually calculate something called f star. You don't, the computer does. And it's simply mean squared regression for say x1 given x2, oh look, it's the type 2 sums of squares divided by type 1. Yeah, type 2 is divided by type 1. Mean squared regression for x1, x2. How much extra unique variation as a proportion of the overall variation. And you know what you do? You never ever touch the defaults on the computer. You just leave it where it is. Because you don't know what you're playing with, and you might end up, again, making your computer do stuff forever. Just leave it alone. Is it a significant enough? Is it enough variance? It doesn't, and everybody's happy. So, in this case, we have eventually this gets down to around 1, and it's like, oh, it's not adding anything significant, we stop. Okay? You can be more than 1, but whatever. You can do it the other way, backwards elimination. Backwards elimination does exactly the opposite thing. It takes all the variables and puts them in at once, and then starts taking them out, the ones that contribute the least amount of explanatory power into Y. So all the variables go in the model. We delete variables that contribute the least until we get to, oh, we've taken out too much. Let's stop here. Okay? So it goes from the smallest r, it keeps taking out the one with the smallest r squared, does the analysis again. Smallest r squared, does the analysis again. Takes one and goes, oh, that was too much. We stop here. This was good. This is a good model. Here's your model. You know what's funny? Almost always backwards elimination and forward selection don't agree with each other.
Huh.
Yeah. It's kind of neat. It shows you that there's other ways to pick them up. What about stepwise regression? This is the one that people think is really sophisticated. What this does is it combines the two. So you go forward, you start by going forward, putting in the thing that has the biggest R squared. And then you check the F star for each variable. And then you keep dropping and adding until if you drop, it doesn't change, and if you add, it doesn't change. Add one in, add another one in. What happens if I take it out? Oh, that's bad. Okay, good, let's put it back in. Now let's put a third variable in. Now let's try to take out the first variable, the second variable, and the third variable, and compare them to the three variable model. And it keeps going until it doesn't change anything. You set a criterion for how big a jump to enter, so it's called F to enter and F to leave. And again, never touch the defaults. Because if you make F to enter and F to leave, if you change them just the wrong way, the computer gets caught in a loop. Puts it in, takes it out. Puts it in, takes it out. That's another thing my students do. I told them specifically, the software knows what it's doing, let it do its job. Professor Brodbeck there. Yes, I'm sorry. I gave them an assignment and none of them listened. Maybe I didn't teach it very well. I did get bad teacher ratings. I thought I was awesome. Then I got them. I went, oh, I'm not nearly as good as I thought I was. It's my first course. But this sounds great, right? And in fact, this will give you something closer probably to a good model. Yeah, F to enter has to be greater than or equal to F to leave. You don't want it. And what people were doing was switching that around to see what happened. And it just gets caught in a loop. And that's not a big deal now when you can just shut the process down. In 1993, it was a big deal because you were using computer time in a time-sharing environment with a mainframe. Okay. See, the thing is, the automatic methods look only at these F's. They're looking simply at R squareds. They don't look at residual plots. I bet there are now algorithms that do this. I just don't know of them. But they don't look at residual plots, forward selection, backward selection, and stepwise, which are the sort of the most common ones you hear about. In fact, a lot of times in papers, you will read a paper that will say, using stepwise regression, because people think stepwise regression is a statistical modeling tool, and it's not. It's a procedure in freaking software. It drives me crazy. Doesn't look at residual plots. It doesn't care about multicollinearity, except tangentially. There's a human element that's really needed here. It doesn't care about nonlinear relationships. It doesn't know. It doesn't look and say, oh, that's not linear. We're not going to use that one. It just keeps going. So, here's the approach that I was taught, and the one time I did this, though, wasn't really for it wasn't for a paper or anything I was writing, it was for, it's a long story. Somebody wanted to know why students were, right, someone said people were coming here back when we had a big co-op thing back in the 90s, and I said, we don't know that, we're just assuming it. So I made up a survey, gave people the survey, and I built regression. And nobody understood it. But at least I tried, because I was young and idealistic and thought people cared. So, you start with a correlation matrix. Just look at the y and all the x's. Do they correlate with each other? What you want ideally is x variables that correlate with with y, but not with each other. So you can immediately usually drop a few of them. Pick a subset. And if it's small enough, if it's say 4 or 5, you can probably just look at all the possible models. I would do exploratory data analysis on all of these things with scatter plots and take a look if we have nonlinear relationships too. And maybe I can fix them. Maybe they're exponential and I can just take the square root of the logarithm or something. Okay? But I pick a subset and if I can, I'll do all possible models. I try all 3 automatic methods, the sort of classics. I try stepwise, I try forward and backward and see if they agree. If they all agree after I've chosen variables by hand, ones that were all linear and they had no outliers, things like that. If I've done that, and then I used, and they didn't overlap a lot, and I tried the 3 automatic methods, and they all agreed, I'd probably say, yeah, it's fine. And the whole time, though, I'm checking, as I said, for outliers, and I'm checking residual plots. The whole time. And then you put it away for 2 weeks and do it again. Because if it's anything complicated at all, you can't remember what it looked like. You're not going to remember what the D's came out with and stuff like that. That's what I would do. And then one time, as I said, when I sort of did it in anger, sort of like in combat, rather than just playing it for class, that's how I did it. And I came up with a model and it agreed both times. So that's what I would do. All right, we're done? Of course it's done. However, on Thursday we'll do some review of, like I'll talk about some major themes.